Hello everyone, in this TRC-car tutorial number 70 we will see that LDMOS exhibits a highly nonlinear specific gate-drain capacitance. We will therefore examine the Miller plateau with a nonlinear Miller capacitor and its effect on drain switching. This is a cross-section of a vertical NLDMOS. When the drain source junction is biased in reverse, which means when the drain voltage VD is significantly higher than the gate voltage VG, a depletion region appears at the PN junction. The depletion boundary is indicated on the cross-section by several dotted lines corresponding to several VDS voltages. The polysilicon gate above the depleted drain region provides a depletion capacitor. The depletion capacitor C-dep behaves like the PN junction capacitor. The Cgd depletion capacitor symbol is noted in dark blue. Around a PN junction, we have the space charge represented here by the electric charges plus and minus Q. For simplicity, I assume that the P and N doping were equal, so the ρ charge density was also equal and the Q charges were distributed over the same distance W on either side of the junction. The electric field can be obtained from the equation divergence of the electric field equal ρ over epsilon. By integrating the constant charge density ρ, the electric field increases linearly from 0 to Emax at x equal W, then returns linearly to 0 at x equal twice W. By integrating the electric field, we obtain the internal built-in voltage VBI generated by the PN junction. Delta V is equal to ρ multiplied by W squared divided by epsilon. Note that delta V is the internal built-in voltage VBI plus the external voltage applied to the diode. The charge Q is equal to ρ WA, where ρ is the volume charge density, W times A is the volume and A is the surface area of the capacitor. Replacing the term ρ with the expression ρ as a function of delta V, we can find the capacitor value by writing Q equals C multiplied by delta V. After simplification, we obtain C equal epsilon multiplied by A divided by W. Thus, the space charges plus Q and minus Q distributed over a distance of 2W are equivalent to a capacitor whose two plates are separated by a distance W, which is half the space charge distance. From the ρ equation, we can obtain W as a function of delta V. Replacing W in the capacitor equation with the expression in red, we obtain a capacitor inversely proportional to the square root of delta V with a factor of K. To get an idea of the nonlinearity, we plotted the curve y equal 1 over the square root of delta V. The gate is driven by a constant current source. Thus, the gate voltage starting at 0 volt increases linearly up to VGSI. When the gate voltage reaches VGSI, the NMOS can drive the drain current ID. Therefore, no current flows through the recirculating diode D, and the drain voltage is equal to the supply voltage Vs. After this specific point, which marks the beginning of the Miller plateau, the drain voltage begins to decrease. The capacitor C-dep is inversely proportional to the square root of delta V. However, since VGD is much higher than the built-in voltage VBI, we can assume that delta V is almost equal to VDG. So we can therefore replace delta V with VDG in the equation. Since VDG is high, the C depth is very low, and the drain dV over dt is therefore high. But as the drain voltage decreases, VDG decreases until it reaches zero. Thus, when the drain voltage is equal to the gate voltage, the capacitance of the C depth is at its maximum value, and that of the drain is at its lowest dV over dt. Then, when the drain voltage is lower than the gate voltage, meaning VDG is negative, the drain dV over dt becomes constant. When the drain voltage reaches 0 volt, the Miller plateau ends and the gate voltage continues to increase. But since C depth reaches its maximum value, the gate slope when Vd equals 0 is lower than the gate slope when Vg equals 0, as shown by the dotted line comparing the two gate slopes. I want to thank you for your attention. After looking at the LDMOS nonlinear Cgd capacitor, in my next heuristic tutorial number 71, we will see how to make a SPICE model of the Cgd capacitor using the p-n junction capacitor model. So, see you soon and stay tuned.